In this video, I'm going to go through the second review sheet for the rational expressions unit. So number 1, state the value of x for which the following is undefined. Remember, in order to find out when a fraction is undefined, we need to take that bottom part, that denominator, and set it equal to 0. So here I'm just going to take 5x plus 3 and set it equal to 0, and solve that equation for x. Because remember, I can't divide by 0, that's what gets me a fraction that's undefined. So if I solve this equation here, I end up with 5x equals negative 3. And remember that 5 is linked to the x with multiplication. So to undo that, I'm just going to use division to get x equals negative 3/5. So if I were to try to plug this into the fraction or that rational expression I started with, the value would be undefined, because I would get that 0 in the denominator. For number 2, they're asking us to express a rational expression in simplest form, and just looking from the top and the bottom here, I'm thinking I'm going to need to factor a little bit. So let's start with the numerator. 7x squared minus 49x. Looks like I could pull out a GCF of 7x there, because 7 and 49 both have that in common, and they both have an x as well. And if I have an x here, then when I multiply it back out, I would get that 7x squared. And if I have a minus 7 there, I would end up with that minus 49x if I were to distribute this back out. So this is what my numerator is going to look like. For my denominator, that's going to be a little bit tougher. I'm even going to give myself a little more room. 2x squared minus 13x minus 7. I still need to factor this, but I can't factor it using that regular AM method because there's a leading coefficient other than 1 in front of that x squared. So what I'm going to do is I'm going to have to use the AC method here, where I multiply the 2 and the negative 7 to get negative 14. And I'm going to find factors or numbers that multiply to negative 14, which add to negative 13. So you could use your calculator to help you out here and just go through a couple of them. But if you look at negative 14 and positive 1, they also sum to negative 13. So I'm going to change this to a factor by grouping problem now by splitting that middle term into plus 1x minus 14x minus 7. Now remember, it doesn't matter what order you write those terms in, you'll still end up with the same answer at the end. So I'm going to group the first two terms, pull out a GCF, group the next two terms. Between a 2x squared and a 1x, I could pull out an x to be left with 2x plus 1. So I'm thinking to myself, I already want that to be in the parentheses for the next set. So I'm going to try to pull out, let's see, negative 14 and negative 7. If I pull out a negative 7, this would have to be a positive 2x, so that when I distribute it back out, I get the negative 14. And this would have to be a positive 1. So what this factors into, if I pull out the 2x plus 1 as the GCF, is 2x plus 1 times my leftovers, x minus 7. So this is what the factored form of the denominator looks like. So now let's substitute back into that fraction. So my numerator is 7x times x minus 7, and my denominator is 2x plus 1 times x minus 7. Now I'm looking for a common factor in the numerator and the denominator that I can divide out and reduce to 1. If I divide x minus 7 by x minus 7, it reduces to 1, so I can get rid of it and just write 7x over 2x plus 1. Notice that my terms in the denominator are linked by addition, so there's nothing more I can do here. With multiplication, it's a little bit easier, but if everything's just connected by addition, you can leave it. Let's take a look at an equation now. Number 3, solve for x. So there are lots of different ways you can solve an equation that looks like this. I'm going to show you a way that will work for all rational equations. So I noticed that my 8x and my minus 2 aren't fractions yet, so I just put those over 1 to make them fractions. But I'm looking for a least common denominator that I can have between all of my terms here. Well, between 1, x, and x, there are steps that I can take to make this denominator x and this denominator x, so my least common denominator is just x. if I multiply by x over x on this side and x over x over here. Remember that x over x is just a fancy way of writing 1, so I'm not changing the value of anything here. 8x times x is 8x squared over x minus 1 over x equals negative 2x over x. Now here's the good part about this. If they all have the same denominator, you don't need to worry about the denominator here, and you can just set the numerators as your new equation. The reason that works is because if you tried to, let's say, multiply this whole equation by x, it would reduce to 1 here, it would reduce to 1 here, it would reduce to 1 there. And all you would be left with are the numerators. So when you have common denominators, you can kind of think about that as just canceling the denominators and writing a new equation with the numerators. Now I'm noticing that this is a quadratic equation because I see an x squared there. So I'm going to try to get it equal to 0 by adding 2x on both sides, so that I have 8x squared plus 2x minus 1 equals 0, and I'm going to solve this by factoring. If you really want to, you could use the quadratic formula, but factoring is always, if you can, going to be a faster method. So I'm going to factor here using the AC method again. I'll multiply the 8 to the negative 1 to get negative 8. And two numbers that multiply to negative 8 but add to positive 2 would be positive 4 and negative 2. So I'm going to split that middle term again to get 8x squared plus 4x minus 2x minus 1. And again, I'm going to do a little bit of grouping here. If I look at those first two terms, they have a 4x in common, to be left with 2x plus 1. And between negative 2x and negative 1, I'm just going to factor out a negative 1 so that that next set of parentheses is still that 2x plus 1. I'm going to keep going up here. I factor out that GCF of 2x plus 1, and I write my leftovers, 4x minus 1. So now that I've factored it and I have two factors set equal to 0, I could split it off and just set each of those factors equal to 0 and solve for my two values of x. So I'm going to set 2x plus 1 equal to 0 and 4x minus 1 equal to 0. I'll subtract 1 on both sides to get 2x equals negative 1 and divide by 2 to get x equals negative 1/2. So that's my first solution. Then over here, if I add 1 to get rid of the minus 1, I'm left with 4x equals positive 1. And when I divide by 4, I'm left with x equals positive 1/4. Now remember, for these rational equations, you always want to look back into your original equation and plug these back in to make sure that they do not make any fractions undefined. Otherwise, they would be extraneous solutions. All right, a lot of work for one problem, but let's take a look at B. B gives us another rational equation, only this time it looks like my least common denominator between everything is probably going to be an x minus 3. So if I just take this 2 and multiply by x minus 3 over x minus 3, I'm going to distribute the 2 into the x and the minus 3. So my first fraction stays the same, 4x over x minus 3. Then 2 times x is 2x. 2 times minus 3 is minus 6. And my denominator is x minus 3 plus 12 over x minus 3. Okay, so all of my denominators are the same. So I'm just going to make a new equation using my numerators. 4x equals 2x minus 6 plus 12. Now I'm lucky this one isn't a quadratic because I don't see x squared anywhere, so I can solve it like a regular linear equation. I'm going to combine the negative 6 and the 12 to make that positive 6, and I could subtract by 2x to combine my x terms on one side of the equation. So I have 2x equals positive 6, or if I divide by both sides by 2, I end up with x equals positive 3. Now remember from the last example I said for each of these rational equations, you always need to plug back into your original equation to make sure it makes sense. And the problem with this one is, when you end up plugging it back in, something weird happens. Right? Notice that for both of these fractions, that denominator is going to equal 0. And remember, if you have 0 in the denominator, that fraction is undefined. So this solution actually doesn't work in our equation. So we're going to reject it because it is an extraneous solution. So if I'm scanning here, I didn't have any other values of x that I solved for. So this is one of those instances where there is in fact no solution to this equation. Sometimes you'll have two answers and you'll be able to reject one of them and not the other, but in this case we rejected our only solution that we found, so there is no solution to this equation. Number 4, factor completely. Alright, so the first thing I noticed here is that there's no GCF between 8 and 27, and there's two terms. So remember, there's two options for two terms. It's either a difference of two squares, one of those dots problems, or one of those SOAP problems using those sum of cubes or difference of cubes formula. If I'm looking at 8, I know 8's not a perfect square and 27's not a perfect square, so this must be one of those cubes problems. So remember your formula for a difference of cubes. Something cubed minus something cubed factors into a minus b times a squared plus ab plus b squared. The reason I said this was a SOAP problem is because that acronym can help you remember the signs and the order which they go in the equation. The first sign you see is always going to be the same as what you started with, so in this case it's a difference. The next sign is always going to be opposite, and the last sign is always positive. Same, opposite, always positive. Okay, so the goal here is to figure out what we were cubing to get 8 and what we were cubing to get 27x cubed. So I recognize 8 as a perfect cube as 2 cubed, and I know that 3 cubed is 27. I do need to remember though that I cubed x to get that x to the third power, so I need to have an x in the parentheses there. So this 2 represents your a in the formula, and the 3x represents your b because that's the second thing you're cubing. So I'm just going to substitute straight into the formula. I'm going to subtract 2 and 3x. A squared would be 2 squared, which is 4, plus a times b, which is 2 times 3x, plus b squared, which is just 3x squared. Notice I have a set of parentheses here so that I remember to square the 3 and I remember to square the x, because all of 3x represents your b, so I need to square all of it. If I simplify a little bit, I'm left with 2 minus 3x times 4 plus 6x plus 9x squared. Once you're done using your cubes formula, unless you have a GCF in this first binomial here, this trinomial in the back will never be factorable. So if you've gotten this far, you're done. Number 5. Solve for all values of x. Let's start with a. I notice that I have 4 terms there, and remember, anytime you have 4 or 6 terms, the easiest way to factor would be factor by grouping. So I already have it set equal to 0, so I don't need to rearrange this at all. If I'm looking at my first 2 terms, the GCF there would be 2x squared, because they're both divisible by 2 and x squared. And I would be left with x plus 9 in the parentheses. And if I factor out a negative 8 from the next 2, I'd be left with x plus 9 in the parentheses again. And remember, this is an equation, so I'm going to keep bringing down this equals 0 in every step. I can factor out that x plus 9, because that's the GCF there. They both have that in common. Multiply that to 2x squared minus 8, and still set that equal to 0. Now, remember before, when we were factoring, the first kind of factoring we always look for is a GCF. Sometimes when it's grouping, you might not think to pull out a GCF first, and if you look, 2, 18, 8, 72, they're actually all divisible by 2. You'll always be able to pull it out in the end. If you notice right here between 2 and 8, that's where your GCF ended up. So you could always pull it out at the end if you want to for factor by grouping. You just need to remember to think to look for it. So I'm going to pull that 2 on the outside, and I'm left with x plus 9 times x squared minus 4. And it's a good thing I pulled that out because x squared minus 4 I recognize as a difference of two squares. So I can factor it one more time to give myself x plus 2 and x minus 2. I've got it set equal to 0, and I've factored completely, so I'm going to separate it now and set all of my pieces equal to 0. I know 2 is never going to be equal to 0, so I don't need to worry about that case, but x plus 9 can be equal to 0, x plus 2 can be equal to 0, and x minus 2 can be equal to 0. If you rearrange these equations a little bit, subtract 9 on both sides to find that x equals negative 9, subtract 2 on both sides to find x equals negative 2, and add 2 on both sides to find x can be equal to positive 2. So these would be your three solutions to this original equation. You should always plug back in the check, but there will never be any values to make anything undefined here because I don't see any fractions, so you won't have any extraneous solutions for these. Sometimes you'll see your solution set written with brackets and just commas separating your x values. So both of these in your x equals form or in your brackets are acceptable to leave your answer in. Something like B gets a little trickier though. This is still an equation that we can solve easily by solving. So I'm going to start by subtracting 8x on both sides. So I have 4x cubed minus 8x equals 0, just because I need one side equal to 0. You could have moved the 4x cubed over there, it doesn't matter which order you do this in. I'm going to try to pull out a GCF of 4x to be left with x squared minus 2, and it's equal to 0. Now before I had a difference of two squares here, but 2 isn't a perfect square, so there's nothing I could do at this point. I'm going to split it off and set both pieces equal to 0. 4x equals 0, and x squared minus 2 equals 0. Well, 4 times a number equals 0. The only number I could multiply to 4 to make it equal to 0 would be 0. Algebraically, the way you could figure that out is just by dividing 4 out on both sides. And for this x squared minus 2, you need to be a little bit more clever with it. So I'm going to try isolating the x by adding 2 on both sides to get x squared equals 2. Now remember, in order to undo a squared, the opposite of that would be taking a square root. And remember, when you take in a square root in an equation, you need to get those two answers, positive and negative radical 2. So you can't simplify that any further. So your three answers here are going to be negative radical 2, 0, and radical 2. Now I just listed them from smallest to biggest, but it doesn't matter what order you list them when you're writing them in brackets. So now we're going to multiply and divide and simplify as much as we can. So usually we're always going to have to start by factoring as much as we can. I already noticed that as a difference of two squares, and that bottom as a regular trinomial that I could use that AM method for. And it looks to me like there's a GCF of x that I could pull out there. So my first numerator becomes x plus 1 times x minus 1. And for this denominator that's a trinomial, I ask myself what adds to positive 5 and multiplies to positive 4. Well, there's only a few sets of numbers you could use that multiplies to 4. 2 times 2, which adds to 4, or 4 times 1, which adds to 5. So that's the magic pair there. Then x squared in my numerator for my second fraction, not much I could do there. But I could pull out that greatest common factor of x in that second denominator to be left with x minus 1. Now here's where the magic happens. You need to look in the numerator and the denominator and try to look for common factors that you could reduce to 1. I noticed that x plus 1 over x plus 1 reduces to 1, and I noticed that x minus 1 over x minus 1 reduces to 1. It doesn't matter that they're in different fractions as long as one is in the numerator and one's in the denominator, because they're linked by multiplication and they're going to end up in the same numerator and denominator anyway. notice that you also have an x squared and an x. If I divide those both by x, that denominator becomes 1, and that x squared just becomes an x. So all you're left with, if you look in the numerator, is just an x, and in the denominator, your last factor is x plus 4. So this is as far as I would be able to simplify it once I've multiplied straight across. For division, it's the exact same process, only you need to remember to keep the first fraction the same, change the sign from division to multiplication, and flip the second fraction before you start multiplying. So you could flip it at any time, but you need to remember that before you start canceling, that you've flipped that second fraction. So let's factor a little bit. I'm going to take that numerator out and factor out a -1 to get x squared minus x minus 20. The reason why I do that is because factoring trinomials is a lot easier when you have a leading coefficient of just +1, because then you could just use that AM method. Ask yourself what adds to -1 and multiplies to -20. So that numerator turns into x minus 5 and x plus 4. In that first denominator, 5x squared and 25x have a 5x in common, and when I factor that out, I'm left with x minus 5. So I change this to multiplication, and that 2x minus 14 is going to end up on top, but if you factor out a GCF of 2 first, you'd be left with 2 times x minus 7. So I'm going to put that in the numerator there, and my denominator is x plus 4. So now it's just multiplication. I look to see what I could reduce on top and bottom. I've got an x minus 5 and an x minus 5, and an x plus 4 and an x plus 4. 2 and 5, there's really nothing I could do with, so I'm just going to multiply straight across. -1 times +2 is -2, and I have that x minus 7, and I still have a 5x in the denominator. So you don't need to distribute the -2. Usually I try to leave it as factors as I can, so this is as far as we can go for this one. For subtraction and addition problems, the goal is to first get a common denominator, and then once we have a common denominator, then we can combine like terms in the numerator. So if I'm taking a look at C right here, they already have a common denominator, so I'm going to combine the numerators. I'm going to take 4x to the 4th plus 4, and I'm going to subtract 8 from that 4. So my new numerator is 4x to the 4th minus 4, because 4 minus 8 is -4, and my denominator is x squared plus 1. Now, once I've combined it to one fraction, I see if there's any simplification I can do by factoring. In that numerator, I notice that there's a GCF of 4, so I could pull that out to be left with x to the 4th minus 1. And I'm getting excited already because I notice that this right here looks like a difference of 2 squares. And in fact it is, because x to the 4th is just x squared squared, and 1 is that sneaky square that is just 1 squared. So I could factor that numerator even further to be 4 times x squared plus 1 times x squared minus 1. And I notice I still have a difference of 2 squares in this x squared minus 1, but it's not going to matter for this case, so I'll stop there. I notice that in my denominator I have an x squared plus 1, and in my numerator I have an x squared plus 1 again. So if I divide those, it would reduce to 1. So all I have left with here is just that 4 times the x squared minus 1 in the numerator. Technically, I do have a 1 in the denominator, but anything divided by 1 is itself, so I'm not even going to write that. For D, it's an addition problem now where I do not yet see common denominators. So I'm going to do a little bit of factoring to see if they do in fact have anything in common. 9x squared minus 4 I see as a difference of 2 squares. That factors into 3x plus 2 and 3x minus 2. And my second denominator looks like I could factor out an x to be left with 3x plus 2. So I want to scan through these and look at what they have and what they're missing from one another. So I notice that my first fraction has a 3x minus 2. So I need to have a 3x minus 2 in my second fraction as well in the denominator. So I multiply by 3x minus 2 over 3x minus 2. And I notice that I'm missing that lone x from my second fraction to my first fraction. So I'm going to multiply by x over x. So my least common denominator here is just x times 3x plus 2 times 3x minus 2, because all of my denominators divide evenly into it. So my new fractions look like negative 3x over x times 3x plus 2 times 3x minus 2 plus 3x minus 2 over x times 3x plus 2 times 3x minus 2. Now, for addition, you don't have to worry about it, but something I will note, if this was subtraction, remember that you would have to distribute it to both of your terms there when you are combining. In this case, we don't have to worry about it, though, because it's good old addition. So negative 3x plus 3x reduces to 0, and the only thing I have left in the numerator is just negative 2. So all I'm left with here is x times 3x plus 2 times 3x minus 2 in the denominator, and just a negative 2 in the numerator. So sometimes we'll have a lot of things that will reduce when we get to this step, but in this case there's nothing I could do with negative 2, so I leave it as such.